The phenomenon of induction and induced EMF have immediate practical applications in a variety of electric circuit devices, including transformers and inductors. As we've seen, when two coils are adjacent, a change in current in one induces an EMF in the other. This is the operating principle of the transformer, and the coupling between the coils is characterized by their mutual inductance. But also a change in current in a single coil causes an induced EMF in that same coil, and the relationship of current to EMF is described by the self-inductance of the coil. A study of energy relationships in inductors leads to the concept of energy stored in magnetic fields. We will study several simple circuits containing inductors, including one that can undergo electrical oscillations. This circuit analysis is fundamental to our study of alternating current circuits later on. So first we're going to look at mutual inductance. An EMF is induced in a stationary circuit whenever the magnetic flux through the circuit varies with time, as we've seen before. If the variation in flux is brought about by a varying current in a second circuit, it is convenient to express the induced EMF in terms of the varying current, rather than in terms of the varying flux. We will use the symbol I, little I, to represent the instantaneous value of varying current. Figure 1 here is a cross-sectional view of two closely wound coils of wire. A current I1, which goes through this coil, in coil 1, sets up a magnetic field as indicated by the arrow line. So here's the magnetic field here. And some of these lines pass through coil 2. Now coil 2, I've drawn it as small here, but that could actually be physically smaller. So you can see that not all the field lines here, all the flux that's going through coil 1, not all of it is going through coil 2. Let the resulting flux through coil 2 be flux 2. So we're going to call these amounts that actually do get through coil, we're going to give that the name flux 2, because obviously it's different to the flux that's going through this coil. The magnetic field is proportional to I1, so flux 2 is also proportional to I1. So the I1 going through here, this flux 2 is proportional to the I1. When I1 changes, flux 2 changes. So a changing I1 through here causes obviously a changing flux 2 through this second coil. This changing flux induces an EMF, E2, so we get an EMF induced in coil 2, given by this equation here. So the EMF that's generated is the number of turns by the rate that the flux 2 is changing, so flux 2 dt. The proportionality of flux 2 and I1 could be represented in the form, so I mean we could actually represent that as some kind of flux 2 equals constant times I1. But it's more convenient to include the number of turns, N2, in the relation. Introducing a proportionality constant, M, we write N2 flux 2 equals M I1. We can divide through both sides by delta T, and we end up with this. Now we can write this equation, using this relationship, as equation 4 here. The EMF equals M di1 by dt. We've rewritten this by replacing the N2 by 2 dt by this term here. So now we don't need to write it as being proportional to the number of turns in 2 and the flux 2 changing. We can completely rewrite this in terms of the current I1 going through these loops here, and we can write it as the EMF is equal to this new constant we've introduced, di1 by dt, so the rate that the current is changing is 1, determines the EMF through this coil here. The constant M, which depends only on the geometry of the two coils, is called their mutual inductance. It is defined by equation 2 here, and may be written as M equals N2 phi 2 over I1, like so. To find our mutual inductance value, we can plug these values in and we'll get that. The entire discussion can be repeated for the case where a changing current I2 in coil 2, so we've got a changing current in here now, causes a changing flux theta 1, so we get theta 1 coming through here, and hence an EMF E1 in coil 1, so now we've got an EMF in here. Now we might expect that the constant M would be different in this case, since the two coils are not in general symmetric, you see that coil is there smaller than that coil, so you might think that the M is different going the other way. But it turns out, however, that M is always the same in this case as in the case considered previously. So a single value of the mutual inductance characteristic completely defines the induced EMF interaction of the two coils. So that M is valid for any condition, whether we're putting the current through one and we're looking at the EMF in here, or whether we're putting the current through this coil one and looking at the EMF in here. It doesn't matter. This M will once we calculated this M, it can be used for both ways. So that's very useful. Now finally, the SI unit, just to complete this now, talking about mutual inductance, the SI unit of mutual inductance, from looking at equation 5, we can see, we can work out the SI units there, is 1 Weber per ampere, which I've written here. So looking at equation 4, we can rearrange for M, like so. We've got voltage over a current multiplied by a time here. If we rearrange it for M, that gives us the units then, voltage seconds per ampere. So we've got two ways of defining the units for this, and in fact what's happened is these two equivalent units are in fact described as 1 Henry. So just to keep it simpler, so in honour of Joseph Henry, one of the discoverers of electromagnetic induction, thus the unit of mutual induction is 1 Henry, which is equivalent to 1 volt second per ampere, or in Webers 1 Weber per ampere, where a Weber is a volt second. So that covers mutual inductance. So here we've got a long solenoid of length L, it's got cross-sectional area A, and is closely wound with N turns of wire, N1 turns of wires. A small coil of N turns, so we've got a smaller coil here, you can see it's got less turns, and of N2 turns surrounds it at its centre, as in the figure drawn below. A current I1 in the solenoid sets up a B field at its centre. The magnitude of the B field is given by equation. Now we've defined this equation before, so the magnetic field going through a solenoid here is given by this equation. So mu naught the magnetic permeability of a vacuum, and then number of turns I1. N is the number of turns per unit length in this equation, so we just replace that. We know what the length is here, and we know the number of turns, so that's N1 over L1, and that's our equivalent. That is what gives us the magnitude of B through this solenoid. Now remembering that the flux is B times the area, the flux through the central section equals BA, and since all this flux links with the small coil, with this small coil here, the mutual inductance is M, as we said before, N2 Phi2 over I1, the current I1. Now we know that the flux in this case, we know that the flux is in case it's BA, so we've got our B here, so we plug in the B here, and we're given the A, so that then reduces to U naught A N1 N2 over L, okay, the length. So if we, for example, if L equals 0.5 meters, A say 10 centimeters squared, well, which is equivalent to 10 to the minus 3 meters squared, N1 1000 turns, and N2 10 turns, we can plug that all in and we can get the M. So we plug all that in and we end up with this M value. So that's an example of how you'd calculate the M value